So I was outside with my students. We were working on sundials and setting those up and watching the shadows. And we were studying moon phases and astronomy. And I just, I pointed out, I said, oh, look, there's the moon. And there's the sun over there. And I kind of looked at my arms and I thought, hang on, that's the geometry of the moon phases. We were at, if it's a right angle, that would have been a quarter moon. And then we kind of incorporate that into our studies. So as much as we could to come out to see the moon at different times during the day, at different phases, and to sort of also pay attention to where the sun was at the same time. Hi, I'm Carolyn Balch, and I'm the author of Engaging Science Labs. And this is just a tiny little window into the kinds of things we do in our classroom. So yeah, if you have the luxury of taking your students outside, even a couple of times during an astronomy unit, to show them this, it is so helpful, and helpful to see how it changes through the days and to see how the geometry changes. I'll show you a model of how that looks from space, and that hopefully will sort of help cement what's going on there. So we use this model. I know it's way out of scale. The moon is too small, the sun is way too small, and they're way too close. But I just wanted to give you a sense of the geometry, okay? So we've got the sun over here, and we've got the moon here, and the moon is going to orbit Earth, and we'll leave the sun where it is relative, okay? And this obviously is Earth, and it's going to rotate on its axis. So no matter where we are on Earth, that's going to be our daytime sky here, and this will be our nighttime sky here. So the moon, in this case, can be up partly during our daytime sky and partly during our nighttime sky. And if I think of these as my arms, and I'm standing on Earth, I can hold my arms, one pointing at the sun, in this case probably my left hand pointing at the sun, and my right hand pointing at the moon. And that's making a 90-degree angle because that's showing me the geometry of where the moon actually is in relation to the sun and me. But as the moon goes in its orbit, let's put it there, it's going to go slowly. It's going to take a whole month to go all the way around, and I've put it about 1/8 of the way from where it was before. Now, if I point to the sun and the moon with my hands, again, my left hand at the sun, my right hand at the moon, can you see how they're making an acute angle? And that, if you look in the sky and see this moon, it's going to be a crescent. You are right. And then it's going to keep going. It's going to go and pass in front of the sun. It does that every month. It almost never blocks the sunlight. We call that, what? An eclipse. It usually passes just below, just above the sun. But if I could see it, and I can't, but I'd have to have special kind of filters or a special telescope. If I could see it and point to it, and I would point, both my hands would be pointing at both, right? Because they're in the same place, and so the angle between my arms would now be 0 because they're in the same place. And I think you can see as we go around, now I'm back to an acute angle, but now my left hand is at the moon and my right hand is going to be pointing at the sun. This is only northern hemisphere. If you're in the southern hemisphere, your arms will be reversed. Everything else will be the same, but it'll be your right and your left arm will be reversed. And then let's say it gets all the way around its orbit, or not all the way, but over to here, okay? And while they look lined up, they rarely are perfectly lined up. So the light from the sun is not blocked by the Earth, and usually the moon's up above or just below the Earth until all the light from the sun hits it. And we get to see the full moon in this case. If Earth blocks the light, that's a lunar eclipse. And over there, when we were talking about the eclipse, that would be a solar eclipse because the moon was blocking the sun's light. Here, the Earth would be blocking the moon's light. But again, those don't happen very often because they have to be perfectly lined up. But now if I'm standing on Earth and I'm pointing one at the sun and one at the moon, now I'm making a 180-degree angle, a straight line, and typically I can't see them at the same time because the full moon is never up during the day. It comes up when? Right at sunset. In fact, most people often notice it then because it's so dramatic. It comes up just over the horizon, full moon, and it spends all of its time in our nighttime sky. And then again, as it continues in its orbit, say right about here, now if I'm pointing at them, I've got an obtuse angle. And this is what kind of moon? This would be a gibbous moon, okay? A waning gibbous. This whole side of the orbit will be waning or shrinking, and this whole side of the orbit would have been waxing. It would be growing from this 0 all the way up to full, and then again shrinking all the way down to 0 back here, or new moon, which is, it's dark because we can't see any of its bright side. And that's just a quick introduction to viewing the moons kinesthetically, using your body, going outside, seeing both the sun and the moon at the same time, pointing to them, and knowing that the angle that your arms are making are going to be the same angle that the sun and the moon are in right now, because you're just going to be demonstrating that geometry on a small scale. To find out more about Engaging Science Labs, check out the website, EngagingScienceLabs.com.